So this is the second lecture, first part of the second lecture. Before we did that when limit was approaching a certain number, but now we are discussing that when limit is approaching infinity, undefined, or when we substitute the limit, for example x minus a, x squared minus a, if we substitute this limit into the function, it is undefined at x equals to a apparently. Although if you do some mathematical calculation, we can get rid of this undefined function, but for instance you can consider it when we substitute limit and function is undefined. So there are various possibilities under which limit x goes to a f of x does not exist. Like I gave you an example here, 1 over, let's say I can give you one more example, limit x goes to 1 over x minus 1. If you substitute x equals to 1 into this function does not exist. You cannot get a number, real number. For example, if one-sided limits are different at x equals to a, then limit does not exist. Like we had in the previous exercise, from left side limit and from right side limit. If both answers are different, then we say limit does not exist. Like here, if we approach towards a from the left side is not equals to limit if we approach towards a from the right side. So another situation where limit may fail to exist involves functions whose value become very large as x approaches a. The very good example for this is this one, like when when a function is approaching towards a specific number 1, its value is becoming very large. So in that case we say that function does not exist, and we use this symbol to denote this. And here you can see the same example. It is approaching towards infinity when x is going towards a. Since infinity is not a real number, the limit above does not actually exist, and we are using the symbol infinity to describe the manner in which the limit fails to exist, and we call this as an infinite limit. So the point where limit does not exist, this is an important point. The point where limit does not exist, we call that there a vertical asymptotes exist. For example, here for this particular function at x equals to 1, or we can say when x approaches 1, this limit does not exist because 1 over 1 minus 1 is 1 by 0, which is undefined. So at that point we say that vertical asymptote exists. When you will draw this function, what is the purpose of this vertical asymptote? When you draw this function, the graph of this function, it will run parallel to that vertical asymptote. It will run parallel to that vertical asymptote, but it will never touch this vertical asymptote. They will run parallel, but they will not intersect or not even touch. So how do we locate vertical asymptote? This is a formal definition of vertical asymptotes. I just gave you an overview or the basic background which is required. We don't need to go into the details, so we will jump into the problems, how to solve this, how to solve the problem, and how to identify. For example, if you have a polynomial means x squared plus 1, any function, not a rational function but any other function like a polynomial. So there is no point where this function is undefined, so it does not have vertical asymptote. Vertical asymptote exists on that point where function is undefined. For this particular function, we cannot find any single point where this function is undefined. So this polynomial does not have any vertical asymptote. So the basic summary of this PPT is a polynomial does not have vertical asymptote because it is defined on all real numbers. Right? Now, which function has vertical asymptote? Normally, a rational function has vertical asymptote, like in the previous slide we saw 1 over x minus 1. So this is a rational function, ratio, division, a quotient function. It has a vertical asymptote because it does not exist on different numbers. For instance, you can see this example, this function does not exist at x equals to 1. So at x equals to 1, this function has vertical asymptote. So if you are given any rational number, if you are given any rational function like this, I am writing it in general, if you are given any rational function, so vertical asymptote may exist on its zeros, where it gives zeros in the denominator. So we put it equals to 0, we solve it for x. So this function will be undefined on these values of x. So we will say that it may exist, there may exist vertical asymptotes. Since a rational function is discontinuous only at the zeros of its denominator. Zeros of its denominator, I have already explained that, where its denominator is approaching or getting 0. So simple procedure for locating the vertical asymptotes of a rational function is we differentiate or we separate rational function into further two functions. We say that n of x numerator and d of x we denote denominator is a rational function. Now d of c equals to 0, we put d of x equals to 0 and we solve it for x, we get some number. Let's say for instance we assume c. So d of c of course will be 0, and if n of c is not equals to 0, then we say that vertical asymptote exists on that point. But if d of c is 0 and n of c is also 0, then we say that vertical asymptote does not exist. Then there may or may not be a limit. So there are chances that limit exists at that point, so we will find that limit. So it will be more clear when we will solve a simple example. For example, I try to solve this example. First of all, we write this function in n of x over d of x. So our n of x is x square x minus 2 over d of x is x square minus 1. We try to find its zeros. As I said, we put d of x equals to 0, which means x square minus 1 equals to 0. If we solve it for x, we get x plus minus 1, or we say 1 and minus 1. Now we see at, first we see at x equals to 1, what is the behavior of d of 1? D of 1 is 0. Now we see the behavior of n of 1. Behavior of n of 1 is 1 square 1 minus 2. So 1 plus 1 minus 2, which is 0. So n of 1 is also 0. So limit may exist at x equals to 1. Now we see at x equals to minus 1, we see that d of minus 1 is 0 and n of minus 1 is not equal to 0. So vertical asymptote exists at x equals to minus 1. So now in the next slide you can see in detail what I did. We put d of x equals to 0, we get two values for x. These are the points of discontinuity of f. Now we apply this formula. We see d of minus 1 is 0, but n of minus 1 is not equals to 0. So the theorem tells us that the line x equals to minus 1 is a vertical asymptote. So x equals to minus 1, this is the vertical asymptote of that function. Now we consider the other zeros. D of x is 0 at x equals to 1 and n of 1 is also 0 at x equals to 1. So there may exist the limit. So we try to find the limit at x equals to 1. So limit x goes to 1. This is our function. We try to solve this. We make the factors x minus 1. We can write this function into this form and this function into this form. So this x minus 1 will cancel out, and this is how we find the limit where vertical asymptote does not exist. So here you can see I have already drawn the vertical asymptote at x equals to minus 1.